Hello everyone, my name is Sankar Perera, and after this discussion, you'll be able to know brief about what exactly reinforcement learning is, what are its application, and what are its expansion and achievements. So, a brief about myself: I am a junior assistant researcher at EPFL. My interest lie in using machine learning and cutting-edge technologies for social good, and I'm very much fascinated by artificial intelligence and its potential ubiquitous use in making lives better for the underserved communities. My core interests lie in deep reinforcement learning and decentralized machine learning. And previously, I've had 4 research experiences and 2 different experiences with international startups. Now, the order of today's discussion will be introduction to the topic, that is reinforcement learning, its application and growth, and then its expansion and achievements. So coming on to reinforcement learning, what exactly reinforcement learning is? So machine learning has three machine learning is categorized into 3 different sections, that is supervised learning, unsupervised learning, and reinforcement learning. So reinforcement learning is one of the 3 basic machine learning paradigm alongside supervised learning and unsupervised learning. Now, what is the meaning of reinforcement? So reinforcement is the occurrence of an event in proper relation to a response that tends to increase the probability that the response will occur again in the same situation. So this was a theoretical definition, but what it exactly means is, for example, if my agent is a car agent, like I'm training a model. So if my car stops on red light and it does not move, so this is something that gives car a positive response while training. So reinforcement will be like the next time when the car sees red light, it will stop. So this is the occurrence of an event. Like if you face this particular environment, then you are supposedly you're supposed to do this. So this is the meaning of reinforcement. Now comes reinforcement learning. So reinforcement learning is the problem faced by an agent that learns behavior through trial and error interactions with a dynamic environment in order to maximize the notion of cumulative rewards. So basically, reinforcement learning works on feedback system, or we can say trial and error interaction. It will be, your agent will be exposed to dynamic environment, and accordingly it will take actions, and on the basis of its action, he'll be rewarded. The agent will be rewarded, either the reward either will be positive or negative feedback, and this later on it piles up to give a cumulative reward. So we need to maximize that cumulative reward in order to outperform our previous models. So reinforcement learning is not a type of neural networks, or nor it is an alternative to neural networks. Rather, it is an orthogonal approach for learning machines. As I said, it emphasizes learning feedbacks that evaluates the learner's performance without providing standard of correctness in the form of behavioral targets. What this means is, in supervised learning, we provide we know the result. We give them the classes or the labels. But in reinforcement learning, we do know the result, but we don't know which path or which action the agent will follow. So reinforcement learning has evolved from supervised learning only, but the only difference between them is the one that I stated now. So this is about reinforcement learning, and in reinforcement learning, the focus is on finding a balance between exploration and exploitation. We just have to make sure that we cover both the cases, like we explore and exploit as well. We are not supposed to over exploit, or we are not supposed to not exploit at all. So like if you are getting to a very good model, then it will be a balance between both. Now, comparison between the three: supervised learning, there are immediate feedbacks. In unsupervised learning, we do not provide any feedbacks. In reinforcement learning, delayed scalar feedbacks are there based on the action. So basically, reinforcement learning has evolved from supervised learning, but there are delayed scalar feedbacks, and which are called as rewards. Now, coming on to the elements of reinforcement learning. So there are, on broad basis, if I talk, there are 3 elements, that is reward function, value function, and model of the environment. Now, we'll understand all these 3 elements in context with this flow diagram. So considering, to understand this flow diagram better, we'll consider a problem where a car is learning to cross, act in a traffic signs, act according to the lights, traffic lights. So this agent is the one which is sent to the environment, like the conditions. So considering in our traffic problem, our agent is the car. Now comes the action. Action is either the car will move or stop. Now environment is the traffic lights, like if the light is green, yellow, or red. And rewards are on the basis of car's action. If the car moves in one particular environment, in a particular environment, the rewards will be given. If car does not act according to the environment, then rewards will be negative. If the car acts according to the environment, then the rewards will be positive. And then comes the state. What is the state of the car? The car is moving or the car is stopped. So this is the complete cycle. So now we'll flow through this. We'll follow these steps. The agent observe an input state. So the car will observe if the light is green or red. Then comes the second step, that is an action is determined by a decision making function which is called as policy. Now this policy will decide either car should move or car should stop. Then the third step is the action is performed. So action is performed like car have two options, either the car can go or the car can stop. Right. The fourth is the agent receives a scalar reward or reinforcement from the environment. That is, according to the environment provided, the action that car takes, it will be rewarded. Information about the reward given for that state / action pair is recorded, which is the value function on a cumulative basis. So now again flowing to the diagram, suppose the traffic light is red, and if the car choose the action to move, the environment is red, action is move, the reward will be negative because in red light the car has to stop, right? And the state of the car will be moving. So our cumulative reward will be negative and it will go down. But our motive is to maximize the reward. So this is a negative impact or the negative feedback. Now, if the light is red and the action taken by car is that the car stops there. Now the reward will be positive, and the reward is positive, the state of the car will be stopped. So this entire can be considered as a positive feedback. So this will enhance and it will reinforce, this will be the reinforcement. If next time the car comes across any red traffic light, it will be forced to stop. So this is the beauty of reinforcement learning, that it learns through trial and error. Now, I guess you'll be clear with reward functions, value functions, model of the environment. So reward function is basically the immediate. We are awarding the agent on immediate basis, like on their immediate action. Then is the value function. Value function is the cumulative stuff. Like if you go through thousands of trials and it's cumulative, like all the rewards are then accumulated, and what is the net sum is called the value function. Then comes the model of the environment, which includes the state and the action. So this is how basically reinforcement learning works. Reward functions defines the goal in a reinforcement learning program, learning problem. So how does reward function defines the goal in an RL problem? So reward function positive, like if the reward function is positive, that means you have achieved your goal. In car's case, if the traffic light is green and car moves, then reward function will be positive. And this is our goal only. Like if there is a green light, then you have to move. So this is how reward function defines the goal in a reinforcement learning problem. And as I told you, a reward function indicates what is good in an immediate sense. That is so true. While a value function specifies what is good in the long run, as value function is the cumulative of reward functions of each and every trial. So this was the basic cycle, how reinforcement learning works. Now coming on to the applications of reinforcement learning. Reinforcement learning has varied applications in robotics, control, game playing, etc. etc. In robotics, if you have ever come across robo soccer, then robots play soccer and they learn through trial and errors. If a robot scores a goal, then he'll be given positive rewards. So the robot will learn that particular techniques which he has followed to make a goal. So this will be a positive feedback for a robot. And apparently, if there is a robot who is goalkeeping, and if he saves the ball by jumping into one particular direction or moving left or right by so and so steps, and if he saves a goal, then he'll be given a positive reward. So he'll get to learn this, that if a ball comes, then I have to move 2 steps left or 2 steps right. So accordingly, the model learns. The robots will learn. And this is the beauty of reinforcement learning. It's really very interesting. Then comes the controls. In controls as well, like in factories, there are various manufacturing or processing units. They learn on trial and error basis. Then comes game playing. It's like tic-tac-toe and chess. If you are a chess player, then you might know that there are various platforms running right now, chess.com and chess24. So how do their models learn? They learn on the basis of reinforcement learning. If you play against the computer and if you win, so the computer will be awarded negative rewards for each and every particular step, like wherever the computer did mistake. But if computer wins, he'll be given positive rewards. So accordingly, if he keeps on winning and winning and winning, then that computer will become a very strong chess player. Now, reinforcement learning is expanding. The reinforcement learning is currently used in the finance sector for evaluating trading strategies. Robots use deep reinforcement learning to pick goods and put them in same container. In Japan, like the robots are working in restaurant as servants. So they all are, learning on the basis of reinforcement learning. Reinforcement learning is now used for business strategy planning. So it has a various, vivid applications. Now, talking about the expansion and achievements that the reinforcement learning has made. So if you are familiar what Go is basically a game. So Google developed AlphaGo. And so AlphaGo is basically an agent that beat the world champion of Go. And the Go is very complicated game and it requires so much logical thinking. So this was a very big achievement because the robot was very close to thinking exactly like a human. The second example can be AWS Deep Racer. So it's basically an autonomous racing car that has been designed to test out reinforcement learning on a physical track. So the Amazon team has been sending this Deep Racer car on physical tracks that the car learns to automatically drive. And IBM is using reinforcement learning to make financial trading, to make financial trades and all these things. And the researchers from Stanford University and Microsoft researchers have fronted deep reinforcement learning for use in dialogue generation. The deep reinforcement learning can be used to model future rewards in chatbot dialogues. So reinforcement learning has been blended with natural language processing, computer vision, wireless technologies, etc., etc. So here are the further more uses of reinforcement learning. Now, coming on to, I'll show you a video by OpenAI, how exactly reinforcement learning is working. And it's about agents learning to play hide and seek. So let's have a look at it.
On Earth, the simple rules of natural selection and competition led to the evolution of increasingly intelligent life forms. Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter. In the last stage of emergent strategy that we observe, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide-and-seek in parallel for many days. They train against each other as well as past versions of themselves using an algorithm called self-play. Coevolution and competition on Earth led to the only generally intelligent species known to date, humans. While this world is far less complex than Earth, we have found evidence that simple rules can lead to increasingly intelligent behavior from multi-agent interaction. We hope that with a much larger and more diverse environment, truly complex and intelligent agents will one day emerge.